So we've been looking at the conditions or the requirements for using evidence to establish causation. And we first looked at time order precedence, and what we saw there was that sometimes it's very straightforward to determine whether or not a cause becomes effect before an effect. In other situations, it's not so clear. And then we've just started to look at this question of association, the idea that there should be an association or a strong correlation between the cause and effect. So we're going to look at several ways of establishing that. We've already looked at cases where the evidence consists of two quantitative variables, and the example we're looking at is job satisfaction and job performance. This is a case where the direction of causation is somewhat ambiguous. It could be one way or the other, or possibly even both ways. So the data in that kind of situation would look something like this. You would have you might have an ID column for your observations, and then you have some kind of measurement of job satisfaction that's probably done with a questionnaire, and you would have some measure of job performance. Again, that could be done by a questionnaire completed by a supervisor, for example, or it could be done by measuring some kind of outputs. And what you're looking for is an association and or a correlation, and the most straightforward case is where you have a linear relationship. So what I've shown you there is a scatter plot with a Pearson correlation of 0.3, and it is in fact a linear relationship. I know that because I simulated the data, but I simulated it to be consistent with what seems to have been found in research on job performance and job satisfaction, which is about a 30% correlation. And we then will do some kind of statistical test. So the most common thing is you'll either do work out a correlation coefficient. So in this situation where you have two quantitative variables, the Pearson correlation coefficient is by far the most commonly used. And in an earlier video I demonstrated a little spreadsheet that I set up that enables you to fairly simply calculate Pearson's correlation coefficient. So I've got my simulated data in there, and the result of the calculation is in that cell just there, along with a whole lot of other stuff. Now, I haven't in this course required you to know how to do Pearson's correlation, and the reason for that is just that when we're doing this rigorously, there's a bunch of things we have to check. It gets a little bit complicated. You need to be a little bit careful, but probably the main thing you need to look out for is outliers. They can be a bit of a problem in some situations. Now, another thing that we commonly do where you have two quantitative variables is we do linear regression, and I've given you the results there, and I talked about these in an earlier video. There's a very close sort of mathematical relationship between linear regression and Pearson's correlation coefficient when you just have two variables. Now, the key thing to note there was that the Pearson's correlation coefficient and the R squared from the linear regression, they tell us that there's a signal there, an association, not tremendously strong, but it's not trivial either. Now, I want to move on to talk about a different setup. So this is where instead of having two quantitative variables, we have two categorical variables. This is a very common situation that arises particularly when you're doing experiments, but also in other contexts, including case control studies, which we looked at in the lecture last week, where so in this case what we have is instead of two quantitative variables, each of our observations, the observations would be individual workers. They are rated in some way. Again, could still be done by questionnaires or some mechanism as either having above average or below average performance, and either being satisfied or dissatisfied with their job. Now, when you have two categorical variables like that, what you end up with is a table of counts. Okay, so we have 82 people here who are satisfied with their job and they're performing above average, 37 who are satisfied with their job but their performance is below average, and then 31 who are dissatisfied with their job but performing above average, and 50 who are dissatisfied with their job and performing below average. And we call the the grey shaded part of that, that is called a contingency table, 2x2 contingency table, and they are very commonly presented with what we call margins, which are typically totals. Okay, so here you have the row totals there, and you have the column totals there, and you have what we call a grand total there. There were 200 observations. We had a sample of 200. Sometimes, for some purposes, the margins of a table might be averages or something, but most commonly they're just totals like that. All right. Now, we have already looked at this, but let me just remind you, we can calculate something called the phi correlation coefficient. And last week I gave you a link to an online calculator you can use for that. I've also this week prepared a spreadsheet that you can use to do those calculations, and I've done a separate video on that explaining how it works. But what it calculates is the phi coefficient, and it calculates the odds ratio, and most importantly it calculates a 95% confidence interval for the odds ratio. And what you're looking for there is whether or not that 95% confidence interval contains 1.0. If it contains 1.0, then you can't make a claim about a significant difference between, in this case, satisfied and dissatisfied workers and their job performance. So some reminders here of how you do the calculation manually for the odds ratio. I've written here a summary of what you can say in this situation. So the confidence intervals only occur, they're only a thing if you are trying to draw a conclusion from a sample to a wider population. So we can say in the sample of 200 workers, okay, there was a medium strength correlation, phi equals 0.3, between job satisfaction and job performance. The odds of a satisfied worker in the sample achieving above average performance were 3.6 times higher than those for a dissatisfied worker. And then, because it's a sample and you're making inference about the population, we can say we are 95% confident this ratio is between 2.0 and 6.5 in the workforce from which the sample was taken. So this bit about the what you have here, that is a statement about the sample, those two things, and this is about the population. It's very important to be clear in your mind what you're talking about there. Okay, so once you move from sample to population, you're moving from exact numbers to confidence intervals. Okay, and because it doesn't include one, if the odds of a satisfied worker achieving above average performance were the same as the odds for a dissatisfied worker, there would be no association between satisfaction and job performance. Okay, so we don't, our aim, if we're going to find ultimately draw a causal conclusion, is we don't want that confidence interval to include one. Now, we have some ways of diagramming association. So the common way is we do it like this. We just draw a line between the two variables, and later we'll see how we might turn those into arrows when we want to talk about causation. In this situation, we have an association, we have a correlation, but so knowing the value of one variable gives us some kind of predictive ability in respect to the other variable, but it's bidirectional. Okay, none of this tells us about causation. The way we can think of it is that these lines here, they indicate a sort of flow of information. Okay, having information about one variable gives you some information about the other. Okay, now I'm going to introduce here another technique we can use with 2x2 tables, and we can use it in other contexts as well, but this is to calculate a confidence interval for the difference between two proportions. Now, we've already learned about what's called the Agresti-Cool method for estimating a confidence interval for a single proportion. What we're interested in here is the difference between two proportions. So we can work out the proportion of satisfied workers who perform above average. That's 82 divided by the total there, 119, and similarly the total of dissatisfied workers who perform above average, which is 31 over 81. If we can work out a confidence interval for the difference between the two proportions, then we might be able to make a claim about the proportions in the population from which the sample was taken. Now, so there's the raw proportions. So that's the proportion. PSA is the proportion of satisfied workers performing above average, and PDA is the performance of dissatisfied workers performing above average. And as you can see, the satisfied workers have a much higher proportion than the dissatisfied workers. And we can calculate the difference between those two proportions, which is 30.6%. What we want to find is a confidence interval for that difference in proportions in the population, the workforce from which the sample was taken. And if that confidence interval doesn't include 0, then we can make a claim about a significant difference in the proportions in the larger population. So I'm just going to state the result here. I've got an appendix in the notes which shows the calculations. I'm not going to have you do the calculations in the next test. They're not outrageously complicated, but there's a number of steps to them, and it's quite easy to make calculation mistakes. And I think at this point in the course it's a little bit more trouble than it's worth to try and test you on them, but it's a really, really useful technique, so it's worth knowing about. And the method I've given you is the best sort of straightforward method that doesn't require sophisticated software for doing this kind of estimate. So here's how we would state the conclusion. Okay, so I've actually calculated the confidence interval, and the calculations are in the appendix. So a representative sample of 200 workers was, on the basis of a survey, classified as satisfied or dissatisfied with their jobs. Okay, so that's one of our categorical binary dichotomous variables. And then on the basis of ratings by their supervisors, the same workers were classified as above average or below average in terms of job performance. Okay, so that's the other variable. Now, then we talk about the proportions in the sample. So a higher proportion of satisfied workers in the sample were rated above average in performance, 69% compared to 38%. So I've just rounded the numbers there. Okay, now here's where we go. So this is all about the sample. Okay. And now we go to an inference about the population. So we are 95% confident that the difference in proportions in the workforce from which the sample was taken, so that's the population of interest, is between 17% and 43%. Okay, so that's about the population. And what you can see is that confidence interval does not include 0. So there is a non-zero difference between the two categories, satisfied and dissatisfied, in terms of their job performance. All right, so I'll leave that there. The next video will look at another case where we have one categorical binary variable and one quantitative variable.